What's the connection between climate change, complex numbers, radioactive decay, coffee cooling, and quantum mechanics? This number. Euler's number shows up in nearly every area of math. It's as fundamental to calculus as pi is to geometry. And it shows up all over the place in science as well. But how did a number that took more than 2,000 years longer to discover than pi become so fundamental? And what were the steps that led to its discovery? The story of E begins with the revolutionary work of John Napier. Napier was born in 1550 in Edinburgh, Scotland. At the age of 13, he was sent to St. Andrew's University. Though his initial interests were in the study of the Christian religion, he eventually developed a deep love for math as well. His pursuit of math would culminate in the invention of an abstract concept that took him more than 20 years to develop: the logarithm. You see, Napier lived and worked in the early stages of the scientific revolution. Copernicus came just before him, and he was a contemporary of Galileo, Kepler, and Tycho Brahe. Newton, Leibniz, and their controversial invention calculus had not yet arrived on the scene. The big challenge of the day was how to efficiently handle all of the new physical data that was being recorded, especially related to the motion of planets. As one scholar described it, these developments involved an ever-increasing amount of numerical data, forcing scientists to spend much of their time doing tedious numerical computations. The times called for an invention that would free scientists once and for all from this burden. Napier took up the challenge. Napier originally published his work on logarithms in 1614 in a book titled Mirifici Logarithmorum Canonis, Latin for the wonderful canon of logarithms. Though our modern understanding of logarithms is inherently tied to it being a function, they were initially conceived by Napier as calculation tables. Tables that turned multiplication into addition and division into subtraction. How? The key idea behind log tables lies in the fact that they provided a map between two types of sequences of numbers: an arithmetic progression and a geometric progression. An arithmetic progression is a sequence of numbers where the difference between any two consecutive terms is constant. In other words, you get from one term to another by adding the same constant each time. For example, the sequence 1, 3, 5, and so on is an arithmetic progression, since the difference between each term is 2. The natural numbers are another example, and any other sequence of numbers that follows this rule. A geometric progression, on the other hand, is a sequence of numbers where the ratio of any two consecutive terms is constant. In other words, to go from one term to the next, you multiply by a constant. So this would be a geometric progression, and so would this, but this would not. By Napier's time, an interesting relationship between these two types of progressions was already known, which I'll illustrate with a table. Consider successive powers of 2. Now place the sequence in the left column and the powers or exponents in the right column. This gives us a table with a geometric progression on one side and an arithmetic progression on the other. Now imagine trying to multiply 32 by 128. We can use this table to do so. First, we locate 32 and find the exponent that corresponds to it. Then we do the same for 128. If we add the exponents, we get 12, which corresponds to the number 4096. Not only does this work for multiplying any two numbers in the left column, but it works for multiplying any number of them together. For example, we can multiply 2 times 4 times 4 times 2 times 2 times 2 times 16 and arrive at 4096 again. In essence, this table has turned multiplication into addition, and it's also turned division into subtraction. It is exactly this same idea that is behind Napier's invention of logarithms. The table here actually appeared in a work titled Arithmetica Integra, published in 1544, just before Napier's birth. It was written by a German monk and mathematician named Michael Stiefel, an interesting figure who supported Martin Luther in his Reformation efforts and also tried to predict the end of the world by applying math to the Bible. In addition to his religious pursuits, though, he was the first person to coin the term exponents, and though the evidence is a bit unclear, this work may have in fact directly influenced Napier's discovery. But Napier's breakthrough goes far beyond this table. What Napier noticed was that the table here becomes far more useful and powerful if the base is smaller. Right now, our geometric progression just involves multiplying by 2 every time. But it's totally useless if we wanted to calculate with any odd number greater than 1, or any other numbers that just don't appear in the table. In fact, the gap between numbers gets larger and larger as we make our way down the table. But look at what happens if we multiply by 1.5 instead of 2. The gaps between numbers get smaller. Or if we multiply by 1.25, they get smaller still. If we get really close to 1, the gaps get incredibly small. But the numbers also grow too slowly to be of any practical use. Napier struggled for years with this problem. How small should the base be? He ultimately decided on this number, 1 minus 10 to the negative 7. Why? He seems to have been following a practice that was common in trigonometry at the time, that of dividing the radius of a unit circle into 10 million parts. With the radius of 1, if we subtract the 10 millionth part, we get the number that is closest to 1. In a similar manner, Napier also decided to start his table at the number 10 million. He then tediously carried out the calculations of multiplying each entry by 1 minus 10 to the negative 7. He didn't cover all 10 million numbers though, as he devised a shortcut to find certain key points and then applied this method to fill in the gaps. Even with his shortcut, it took Napier 20 years and 90 pages of tables to complete this monumental task. He first called the numbers in the arithmetic column artificial numbers, but then decided a better term would be ratio numbers, or in Latin, logarithmus, derived from the Greek logos and arithmos. Now, it's impossible to overstate just how useful Napier's logarithms were to the scientific community. Calculations based on celestial objects that took astronomers and navigators days to perform were now able to be done in mere hours or minutes. These days, trying to get rid of your private info on the internet can similarly take a crazy amount of time. But with today's video sponsor, Incogni, a task that could take you hundreds of emails and weeks to complete can now be done with just a few clicks. Incogni is a service that automatically removes your personal info from the internet. You see, there's tons of data brokers out there that collect all sorts of different information about you and then use it to make a profit by selling it to anyone willing to buy. The consequence? Things like your name, date of birth, phone number, address, and family details can end up online, available for anyone to see. Of course, it's possible to figure out who exactly has your data, contact each one of them, and ask them to remove your personal info. But who has the time or the knowledge to do all that? With Incogni, a stressful, time-consuming task can now be done with just a few clicks. All you have to do is create an account, give them approval to remove your info, and then they do all the work for you. They automatically reach out to data brokers on your behalf using whatever is the most successful method in your country. Just a couple months after signing up, they've successfully removed my personal info from over 380 different places and saved me hundreds of hours. So if you're at all concerned about data privacy like I am, I highly recommend you check out Incogni. You can sign up for an annual plan for yourself or for their family plan to protect your whole family. To take your personal data back with Incogni, just head over to incogni.com/abidebyreason or click on the link down below. And when you do, be sure to use the code abidebyreason to get 60% off an annual plan. Thank you to Incogni for sponsoring this video. And now back to the story of E. Napier's logarithm differs from the modern one in a few respects. It would take another 150 years or so before the modern definition would be clarified and the number e would be fully uncovered. But Napier was close to discovering it. Or rather, to be more precise, Napier came incredibly close to discovering the number 1 over e. Napier's logarithm was equivalent to this equation. If we divide n and l by 10 million, this amounts to just rescaling variables. Then relabeling, we get this equation, which as you can see is incredibly close to 1 over e. So Napier's logarithms are essentially equivalent to the modern logarithm with a base of 1 over e. But this is only apparent through modern eyes. Napier may have been close to discovering e, but he in fact did not get there. Over the next few decades, several other figures came close to discovering e as well. Most notably, Christian Huygens, a famous Dutch scientist who, while studying the relationship between logarithms and the curve y equals 1 over x, calculated the logarithm of e to 17 decimal places. But the number just appears as some constant in his work, and Huygens didn't realize that it had any special significance. The true initial discovery would eventually come about 50 years after Napier's work, from a mathematician working on an entirely different topic. Jacob Bernoulli was born in 1655 in Basel. In obedience to his father's wishes, he attended the University of Basel to study theology and philosophy, in preparation for life as a cleric. As time passed, though, he began to develop a deep interest in math, physics, and astronomy. As he would describe it, against my father's will, I study the stars. After completing his degree in 1676, he traveled across Europe to continue his studies with leading scientists of the time. Eventually, in 1683, he returned to the University of Basel and was offered a position teaching math and physics, a position he would hold for the rest of his life. That same year, Jacob Bernoulli began studying compound interest. He imagined a simple scenario. Suppose you encounter a very generous bank that offers 100% interest, calculated once a year. You decide to give it 100 coins. So at the end of a year, your 100 coins becomes 200. Now suppose that the bank calculates interest at 50% every 6 months instead. In this case, your 100 coin investment becomes 150 at 6 months, and after another 6 months, the 150 earns an interest of an additional 75. So the total you have after a year is 225. If you then consider the bank applying 25% interest 4 times a year, you get this total. And you can also consider monthly, daily, and any other number of intervals. The formula that describes this pattern is the compound interest formula. And what Bernoulli asked was, what happens if you take the limit of this expression as n goes to infinity? You find that the 100 coin investment you made turns into this number, and the number e suddenly appears. It is here that we can say Bernoulli was the first person to discover the number e, but he didn't call it that, nor was he able to actually calculate it with any significant precision. In fact, he was only able to go so far as to say that this limit must exist between 2.5 and 3. Bernoulli's work appeared in a scientific journal called Acta Eruditorum, which unfortunately seems to exist only in Latin with no modern translations. Though Bernoulli provided the first true definition of e here, he had no clue that it was connected to logarithms in any way. That connection would require another 50 years or so, and the arrival of one of the greatest mathematicians of all time. Leonhard Euler was born in 1707 in Basel, just like Bernoulli. He was taught mathematics from a very young age by his father, who was a former student of Jacob Bernoulli at the University of Basel. When Euler was just 13, he began attending this same university. And although Jacob Bernoulli had passed away at this point, Euler received math lessons from Jacob's younger brother, Johann. As Euler described in his autobiography, the famous professor Johann Bernoulli made it a special pleasure for himself to help me along in the mathematical sciences. He offered me free access to him every Saturday afternoon, and he was gracious enough to comment on the collected difficulties. which was done with such a desired advantage that when he resolved one of my objections, 10 others at once disappeared, which certainly is the best method of making happy progress in the mathematical sciences. To say that Euler was one of the greatest mathematicians of all time is itself an understatement. He published more than 800 books and papers during his life, and almost half occurred after he went completely blind. His works are so vast that scholars are still editing them today. So in a sense, though he died in 1783, he's still publishing today. As another great mathematician said, read Euler, read Euler. He is the master of us all. In fact, much of our modern math notation originates with him. So it should come as no surprise that the notation for E does as well. The first mention of E occurred in 1731 in a letter Euler wrote to a fellow mathematician. Though it's a bit uncertain, Euler likely chose E as a symbol since A, B, C, and D were commonly used by mathematicians at the time, and E was just the next available letter. Alongside his many other works, he explored the properties of E over the years and made many discoveries. It eventually appeared in Euler's work on mechanics, written in 1736. And in 1748, he published his full treatment in a work titled Introduction to Analysis of the Infinite. Euler proved that E really was the limit that Bernoulli discovered earlier, and he calculated it to 18 decimal places. Unfortunately, he just wrote the number down without explaining how he actually did the calculation. He also generalized Bernoulli's definition and turned it into the general exponential function. He then used the binomial theorem to prove that it equaled this series. At this point in time, exponential functions were well studied, and it was already known that the exponential function was merely the inverse of the logarithm, but their own unique independent definitions had not been fully developed yet. Euler was able to provide it for the first time. He defined e to the x as this, and the definition of the natural logarithm was this. The fundamental connection between e and the logarithm function was firmly established. This definition allowed Euler to discover a unique property of the exponential function. It equals its own derivative. Taking the derivative, he got this, which is equal to the original expression. So if you plot e to the x, you can see that it has a property that no other function has. For any point you pick, the height, the slope, and the area under the curve all equal the same thing. Additionally, with x equal to 1, Euler was able to show that E equals the following series. He even wrote continued fractions of E and proved that E is an irrational number. Finally, by using his series representation of e to the x, he was able to discover one of the most beautiful expressions in all of mathematics. He substituted x times the imaginary number I into the exponent here. Simplifying gives this expression. And then grouping all the real terms together and the imaginary terms together, he got this. He knew that the series in the parentheses here equaled cosine and sine, and he arrived at what we today call Euler's formula. By substituting in x equals pi, he arrived at this beautiful expression. With all these discoveries then, it's no surprise that E has come to be known as Euler's number. This was just the beginning of E's appearance in mathematics though. After Euler's work, it fairly quickly began appearing in all sorts of other areas of math and science as well. But why? How did a number that took more than 2,000 years longer to discover than pi become such a fundamental concept in both math and science? Well, as we've seen so far, E isn't just some random number. Just as pi isn't just a constant that happens to be around 3.14, E is also not just some constant that happens to be around 2.718. It's a constant that naturally was discovered in the development of math and science. The reason? Well, I think there are many, but here's one way to look at it. Whereas pi is fundamentally related to the nature of a circle, E is fundamentally related to continuous growth and change. A clear, rigorous understanding of geometry was available to the ancients, which is why pi shows up so much earlier in history. It is only after a similarly clear understanding of motion and change was developed in the scientific revolution that the nature of E could be truly discovered. Moreover, due to the fact that E is the base of the natural logarithm function, this allows us to write an exponential function with any base in terms of E. So anytime we are trying to describe something undergoing exponential growth or decay, E will inevitably show up. Now, this is of course just a choice that we make, but it is a very convenient choice, and it makes things a lot simpler, cleaner, and provides an extremely useful reference point. In a sense then, just as we can consider every number as a scaled version of 1, and every circle as a scaled version of the unit circle, we can consider also every type of growth or decay as a scaled version of E, which is exactly why E shows up in so many areas of math and science. In the mathematics of describing continuous change and quantifying uncertainty, as well as the science of radioactive decay, Newton's law of cooling, trying to understand the severity of climate change, and probing the deepest layers of nature. A big thank you to all my Patreon members for their generous support, and thank you for watching.